Just think for a second about all the metal objects you use every single day. Your car door, the kitchen sink, even a simple filing cabinet. They're all these complex, three-dimensional things, right? But what's really wild is that every single one of them started out as just a simple, flat sheet of metal. And the journey from that flat sheet to a finished part, well, it's a hidden world of incredible engineering, and we're about to dive right in. I mean, just look at this stuff. You've got cones, domes, parts with these really intricate holes and stiffening ribs. It almost seems like magic. But I promise you, every single one of these amazing shapes was once a totally flat, boring, two-dimensional piece of metal. So that's the big question, isn't it? How on earth do you do that? How do engineers take a flat sheet and convince it to become these amazing objects? Well, we're going to explore the three main challenges they have to solve and some of the really clever solutions they've come up with. Okay, so first things first. Any project, I don't care what it is, starts with cutting your material to the right size. In the world of sheet metal, that critical first step is a process called shearing. You can think of shearing like a giant, super-powered hole punch. You've got a punch on top, a die on the bottom, and the sheet metal gets sandwiched in between. When that punch comes down, the intense pressure creates something called shear stress, and it basically just slices right through the metal. But, getting that slice just right is a lot harder than it sounds. And this is why it matters so much. A bad cut is a really big deal. It's not just ugly. It creates this rough, fractured edge that gets work-hardened. That's just a fancy way of saying the metal right along the cut becomes super brittle, and it's filled with these teeny tiny microscopic cracks. And if you try to bend that piece later on, those little cracks can grow and spread, causing the whole part to just fail, kind of like the tear you're seeing right here. So the solution to this is a really brilliant process called fine blanking. See, a normal cut just punches straight through, and you get that rough edge. But with fine blanking, there's a crucial extra step. Before the punch even moves, a special V-shaped ring on the die clamps down hard on the metal right next to the cut line. This is the whole secret. It locks the metal in place so it can't be pulled or fractured. It forces a clean slice. And the difference is just night and day. Seriously, look at this. On the left, that's your conventional cut. See how rough and fractured it is? But on the right, that's the fine blanked edge. It is perfectly smooth, perfectly square. Having that high-quality edge is absolutely essential for everything that comes next. All right, so now that we have a perfectly cut piece of metal, a blank, we can move on to the next big challenge, taking that flat 2D shape and giving it a third dimension. And we do that through the art of the bend. Bending is absolutely fundamental. It's how you make everything from a simple little bracket to the entire body of a major appliance. And what's really cool is that bending adds a ton of stiffness and strength to a part without adding any more weight. But here's the catch. You can't just bend metal however you want. As you bend it, the outer surface is getting stretched. And if you try to make that bend too tight, the tension just becomes too much, and the material will literally crack. Every type of metal has what's called a minimum bend radius. It's the tightest corner it can handle before it breaks. Okay, so even if you don't crack the metal, there's another, more sneaky problem you have to deal with. Now, this quote sounds a bit technical, but the core idea is actually really simple. Metal basically has a memory. It's kind of like a really stiff spring. When you bend it, it doesn't want to stay perfectly in its new shape. And this tendency for the metal to try and go back to its original flat shape is the single biggest challenge in bending. It has a name, springback. So imagine you bend a part to a perfect 90-degree angle. The second you release the tool, it might spring back to, say, 92 or 93 degrees. And just like that, your part is ruined. So how would you fight something like that? Well, engineers have two main tricks they use. The first one is pretty straightforward. It's called overbending. If they know a part is going to spring back by 3 degrees, they'll just bend it to 87 degrees to begin with. That way, it springs back to a perfect 90. The second method, coining, is a bit more aggressive. It uses a massive amount of pressure to literally crush the metal at the bend, which permanently sets it and erases its memory of being flat. So, we've figured out how to cut and how to bend. But simple bends aren't going to get you a cooking pot or a soda can. For those really deep, complex shapes where the metal has to stretch and flow in all directions, we have to tackle our third and final challenge. This is where a process called deep drawing comes in. You start with a flat, circular disc of metal. A punch then pushes that blank
down into a die cavity, forcing the metal to stretch and flow up around the punch into a deep cup-like shape. This is exactly how we get things like our kitchen sinks, pots and pans, and yeah, all those aluminum beverage cans.
Now, there's another really cool process for making round parts, and it's called spinning. Instead of a big punch and die, you take a flat metal disc and clamp it to a rotating form, which is called a mandrel. Then a tool comes in and slowly presses against that spinning disc, gradually shaping it over the form. It's almost like throwing clay on a potter's wheel, but with solid metal. It's amazing to watch.
And this is the kind of stuff you can make with it. Spinning is perfect for creating these axis-symmetric parts, which is really just a fancy way of saying they're perfectly symmetrical around a central axis. Think cones, bowls, and all sorts of decorative pieces. A lot of times, this method is cheaper for smaller batches because the tooling is way less complicated than what you need for deep drawing.
Okay, so we've covered the basics of cutting, bending, and forming, but let's look at where this technology is headed, because the future isn't just about shaping a piece of metal anymore. It's about creating smarter parts before you even start to form them. And that brings us to this absolutely brilliant idea, tailor-welded blanks. Now, this concept is going to sound totally backwards at first. Instead of starting with one sheet of metal, you take several different sheets. Maybe they have different thicknesses, maybe they're even different types of steel, and you laser weld them all together first while they're all still flat.
So here's how it would work for something like a car's side panel. First, you cut, or blank, 5 separate individual pieces. Then, you use a high-precision laser to weld all those flat pieces together into one composite sheet. And only then, once you have this tailored blank, do you put it in the press and stamp it into its final 3D shape.
So you might be asking, why go through all that extra trouble? Well, because this is a complete game changer. You're not just designing a part anymore. You are designing the material itself. For a car door, you can use a super thick, high-strength piece of steel right where the pillar is for crash safety, but then use a much thinner, lighter piece for the main panel. You get to put strength and weight exactly where it's needed and nowhere else. And the result is a part that's lighter, stronger, safer, and cheaper to make. So, from that very first cut to the final complex bend, the journey from a flat sheet to a finished part is this incredible story of ingenuity that's just hidden in plain sight all around us. So maybe the next time you open your car door or grab a soda can, take a second and think back to that simple, flat sheet of metal. What other secrets are hiding in the objects you use every day?